This is the last in a three-part series on review of random variables. Today's topic is binomial and geometric distributions. So a binomial setting consists of n independent trials of the same chance process. Think about flipping a coin 100 times or rolling a die 20 times, each resulting in a success or a failure with probability of success p on each trial. The count, x, of successes is a binomial random variable. Its distribution is called a binomial distribution. Here are some examples of binomial settings: tossing a coin and considering whether it comes up heads or tails. So their successes are heads, or you can define successes as tails. Checking items from a production line, where success would be they're not defective and failure would be they're defective. Phoning a call center, success, the operator is free and can take your call. Failure, no operator is free. So a binomial distribution, like all distributions, has some conditions that need to be met to make it the appropriate distribution to use. First, it needs to be a binary situation, meaning that each observation falls into one of two settings, either success or failure. Second is independence. Each of the n observations have to be independent of each other. In other words, knowing the outcome of one trial doesn't affect the results of any subsequent trials. Flipping a coin and recording whether it's a head or a tail is an independent event, because each flip of the coin is independent. Just because I get 5 heads in a row doesn't mean the next one is going to be a head. The probability is still 0.5 that the next one is going to be a head. And so the number of trials n is fixed in advance. So I decide to flip a coin 20 times and count how many heads I get. And last but certainly not least, the S for success. The probability of success, which we call P, is the same for each trial. Every time I flip the coin, the probability that I get a head is 0.5. And so those initials, B for binary, success, failure, I for independent, N for number of trials fixed in advance, and S for success. So VINs may help you remember that. If you pull out your yellow formula sheet for the AP, you'll notice that these formulas for binomial are on here. So it says if X has a binomial distribution with parameters n and p, so we would write this: X follows a binomial distribution with parameters n and p. The probability, so this one right here says the probability that X equals k. For example, the probability of getting exactly 3 heads when I flip a coin 10 times would be 10 choose 3. Probability of success, which here is 0.5 to the 3. Probability of failure, which also happens to be 0.5 to the n minus k, or 10 minus 3, or 7. Mu of x, the mean of x, or the expected value of a binomial, is just n times p. If I flip a coin 100 times and the probability of getting a head is 0.5, then I expect in the long run to get 50 heads. The standard deviation of a binomial is given by this formula. If I use a binomial distribution as an approximation for a normal, the mean of the p-hats will be centered at p, and the standard deviation will be that. All right, let's look at an example. A recent survey conducted by the College Board of high schools that offer AP programs revealed that 65% of the schools surveyed favored a later date for the AP test. If 20 schools that offer APs are randomly surveyed, what is the probability that 8 of them favor a later AP date? Well, let's check to see that this is indeed a binomial situation. We sort of have a feeling that it is, because that's what we're talking about right now. But the B, binary. Are there exactly 2 successes, success or failure? So here, we were told to let my random variable x be the number of the sample that favor a later AP date. So success is favor a later AP date, failure doesn't favor. Independent. Well, it says that, let's see. It says that the schools were randomly surveyed. So the fact that one school did not favor a later AP date should have no effect on another school's feeling about a later AP date. Number of trials fixed in advance, and it says that we asked 20 schools, so our n equals 20. And the probability of success for each trial is given to us as 0.65. So we can say that the random variable x, which we define to be the number in the sample that favors a later AP date, we can say that that follows a binomial distribution. The parameters are n and p, so my n is 20, and my p is 0.65. My question of interest was, what is the probability that 8 of them favor a later date? So the probability that x equals 8, I could use the binomial formula that we just looked at on the formula sheet, which is right here. So I could say that's equal to 20 choose 8 times success, which was 0.65 to the 8, failure, which was 1 minus that, or 0.35 to the 20 minus 8 is 12. Or I could just go to my calculator, and so I'm going to do that. I'm on a calculator page. I go Menu, Statistics, Distribution. I need to arrow down, whoops, excuse me, let me escape out of there. Menu, Statistics, Distribution. I need to arrow down until, oh, I keep doing this, sorry. Menu, Statistics, Distribution. Let me try arrowing down over here. And I want to get till I have binomial PDF because I want the success on exactly 8 trials. It asked me the number of trials, which was 20. The probability of success was 0.65. And the x value, if I don't put optional, it gives me the probability for each of them, but I want to know the probability of exactly 8 successes, and that's my answer there. So let me go back here, and let me just show you the work that you need to show for that. So let me move this up. And so basically define your random variable if they haven't defined it for you. Hit that here. State the distribution and its parameters. Here the parameters are n and p. Show what it is you're finding, and then you can go to your calculator to get that probability. And then just a quick sentence in context, the probability that 8 of the 20 randomly surveyed schools favor a later AP date is about, that should be a 0.014. Okay, our next question, what is the probability that more than half of the randomly surveyed 20 schools that offer APs are in favor of a later AP date? Okay, so this is still the same situation. So our x, our random variable, we defined over here as being the number in the sample that favor a later AP date, so we don't have to redefine that. And we actually don't have to redefine, but it's good to put it down for ourselves. So we've got a binomial distribution with n20 and p 0.65. And this time the question of interest is, what's the probability that more than half are in favor of a later AP date? So the more than half, so if 10 were half, that would be the probability that x is greater than 10. So that's going to look like the probability x equals 11, or the probability x equals 12, plus probability x equals 20. Okay, so this is not a PDF, this is a CDF. So we're going to use the CDF command because we have an inequality here. So we want to get the probability of 11, 12, all the way up to 20. Let's flip back to the calculator. We'll go Menu, Statistics, Distribution. We'll arrow down now until we get to Binomial CDF. See if I can get it first time. All right, it asks us the number of trials, which is 20. I'll tag down the probability of success, 0.65. The lower bound, so we wanted the probability of more than 10. So more than 10 starts at 11. And the upper bound, the maximum number of successes I can have is 20. And there's my value. Let's flip back to our problem. And so I showed the work that you need to show here. So again, we want to define our distribution and its parameters, show what we're finding the probability of. We can go to our calculator and get that probability, and then just write a sentence in context. Okay, on we go. Now, if a count x has a binomial distribution with number of observations n and probability of success p, then the mean, another name for the mean is the expected value, so we could write this b of x or mu of x equals n times p. We already talked about that, and you saw it's on the formula sheet. And the standard deviation of the random variable x is just square root of np, which is the number of successes, times 1 minus p, the number of failures. So let's look at an example. So in the previous problem, we said, what is the expected number of schools and the standard deviation for the number of schools that favor a later AP date? Well, we knew that the distribution was binomial with n20 and probability of success 0.65. So our expected value, E of x, or mu of x, will equal n times p. Our n was 20, our p was 0.65. And we know that our standard deviation of x, well, I'm just going to show you the answer here. And again, that's just a calculation you can do on your calculator on a calculator page. So we've got, for some reason I had two of those. So we see here that the expected value, or the mean, is 13, and the standard deviation is about 2.13. So in context, we'd expect about 13 of the schools that offer AP to prefer a later test date. And the standard deviation in context, if the survey were repeated many times with random samples of 20 schools who offer the AP, the number who prefer a later date would differ from 13 by an average of about 2.13. Okay, so we've looked at binomial setting when we have a PDF example, exactly 8 successes, a CDF where it's an inequality, and we looked at the mean or expected value and the standard deviation of a binomial. All right, how about using binomial distributions in statistical sampling? So binomial distributions are important in statistics when we want to make inference. So we've been doing that lately. We've been doing statistical tests for population proportion. So we know that when we're sampling without replacement, we can use a binomial distribution as long as our sample, that's little n, that our population is at least 10 times our sample size, so big N is our population size. And we also know that in order for a normal model to be appropriate, that the number of successes and the number of failures has to be at least 10. So let's take a look at that. And if that case holds, then the mean of our distribution will just be NP, and the standard deviation will be NP times square root of 1 minus P. And so let's look at, that's not the one I want. Let me, no, actually I want this one. Let me flip into one that we looked at in class earlier. So why that condition that the number of successes and the number of failures have to be at least 10 in order to use a normal distribution to model binomial data? So here, I did a binomial distribution in which 10% of the population of marbles is yellow. And so if we draw samples of size 10 from this population, we know that we'll have a binomial distribution where our n is 10 and our probability of success, p, is 0.1, right? So for this particular simulation, every time I hit Control R, I'm going to get a new random sample. And you should see that the expected value, n times p, looks to be where we would expect it at 1. So it would not be appropriate to model this distribution with a normal model because, let me undo that, because it's extremely right skewed. That should make sense to you because if the expected value is 1, I don't have enough room, I'm bounded by 0, so I don't have enough room for it to bell out to get an approximately normal distribution. Let's look at what happens when I bump the sample size up to 30. The reason I chose 30 is students think that that's a magic number because when we looked at our distribution of sample means, the central limit theorem kicked in at 30. Let's see what happens with this. So now we still have a binomial distribution. Our n is 30, but our probability of success, p, is 0.10. And so we look at it and we see that the mean of the distribution, n times p, or 30 times 0.1, should be centered at 3. And again, it's not as right skewed as the other distribution, but I can see that having a center at 3, it's still pretty skewed. So again, remember, we're checking why successes and failures have to be at least 10 in order for a normal model to be appropriate. So now we bump our sample size up to 100. So if I multiply n 100 times my probability of success 0.1, I'm going to get the 10 that I need. And also when I multiply that by 0.9, I obviously will have a value bigger than 10. So let's look at that distribution. So here we see that the expected value should be centered at 10. And I have enough room on each side to get that approximately normal distribution. All right, so that was just a reminder of why we need that condition that the successes and failures have to be at least 10 to model a binomial distribution with a normal model. Okay, now we're going to look at the geometric distribution. It's very similar to the binomial distribution. In fact, there's only one main difference. In the binomial distribution, we have a fixed number of trials. I'm going to flip a coin 20 times. In a geometric setting, we don't have a fixed number of trials, and the possible values of the random variable start with 1, 2, 3, all the way up to n. The reason they start with 1 is because our object of interest is to obtain the first success. So the random variable x can be defined as it counts the number of trials needed to obtain the first success. And possible values, as I already mentioned, of a geometric random variable, unlike the binomial that starts with, so if x follows a binomial distribution with parameters n and p, then the possible values of the random variable are no successes, 1 success, 2, dot, 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 all the way up to n. If my distribution follows a geometric, if my random variable x, follows a geometric distribution, then there is no fixed number n. So my only parameter is the probability of success. And since I'm waiting for the first success, I start at 1, 2, 3, 3. And theoretically, I may have to keep going infinitely to get that first success. All right? So the conditions for a geometric distribution, again, much like the binomial, first one's the same. Observations fall into one of two settings, success or failure. The observations have to be independent of each trial is independent of each other. Now this is where we had the bins. So we had an n here for binomial. The number was fixed in advance, the number of trials here. The goal is to count the number of trials until I get my first success. And the last one stays the same, but the probability of success has to stay the same for each trial. So instead of the bins for binomial, we've got the bits for geometric, all right? So the main difference here is that our object of interest is how many trials we have to do to get our first success. So let's look at an example. So Holly, Mrs. Negro's golden doodle, loves to play catch. Unfortunately, she, that's Holly, not Mrs. Negro, is not particularly adept at catching, as her probability of catching the ball is only 0.23. Assume that the outcome of each toss is independent. How many tosses should Mrs. Negro expect it to take for Holly to catch the ball once? All right, well, let's look at some keywords here. How many tosses should Mrs. Negro expect? So what are we looking for here? An expected value or a mean? And now to catch the ball once. So really what we're wondering is, what is the mean number of times before she gets her first success? Now, here's the work that you need to show. Unfortunately, the formula for the mean of a geometric, mu of x equals 1 over the probability, is not on the formula sheet, so that's one that you're going to have to commit to your memory. And so we got an expected value, so we defined our random variable, we defined the distribution and its parameter, it's geometric with a parameter p of 0.23. We wrote out what we were finding, the expected value, our first level substitution for 1 over p, and the sentence in context. On average, it would take Holly between 4 and 5 tosses before she caught the ball for the first time. All right. Follow up to that, what is the probability that it takes Holly more than 6 tosses to make her first catch? Okay, so what's that going to look like? All right, so ones like this. So again, a random variable x, still geometric, probability of success, still 0.23. And our value of interest is the probability that it takes her more than 6 tosses before she has her first success. I like to, when I have an inequality, I like to put a little number line on there. So more than 6 would be 7, 8, 9, and remember that can keep going. So since I can't count from 7 up to theoretically an unbounded value, another way of looking at this is the probability x is greater than 6. The only values I haven't taken into consideration are down to 1. So it's these values here. So that's the same as the probability 1 minus the probability that x is less than or equal to 6. Okay? And so I'm going to go to the calculator to do that. It's geometric. It's going to be a CDF because I have a range of values I want to compute. So I'm going to go back to my other screen, and I'm going to go to Menu, Statistics, Distribution. I know I want a geometric distribution. I want a CDF because I have an inequality. And there we go. All right, it asked me the probability of success. That's my only parameter. My lower bound, okay, so we were going to do 1 minus the probability that x is less than or equal to 6. So my lower bound would be 1, my upper bound would be 6. When I get that, my actual answer is 1 minus that value, so I'm just going to go up and capture that. And so my probability is actually 0.2084. Now we know that the probability that x is greater than 6 could happen at the 7th, 8th, 9th, the 100th, but those probabilities get smaller and smaller as I get further away from the expected value. So I'm going to show you what you actually could do on here. I'm going to go back to geometric CDF, and I'm just going to do the problem success is 0.23. So we wanted the probability that x was greater than 6. So our first success would happen on the 7th. Now I can't put infinity in there, but I'll put a big number in there because the probabilities get so close to 0 that far away. And notice that I got the same value there. So I'm going to go back to here, show you the work that you need to show, define your distribution, state the parameters for it, define the problem that you're finding, give your answer, and give a short sentence in context. Okay, before I wrap this up, oftentimes you'll get a multiple choice question, and instead of the answer being computed, it's given in formula form. So take a look at this one. It says a machine manufactures glass bottles of which 5% are defective. Okay, so I know that 5% is going to be my probability of success. If a random sample of 7 bottles, let me write that down, n equals 7, is taken from the production line, count the probability that at least 2 are defective. At least 2 are defective. Well, this looks like a binomial setting to me. There's 2 outcomes, defective or not defective. There's a fixed number of trials, n equals 7. Probability of success is the same from outcome to outcome. All right, but I want to know the probability that x is at least 2. So at least 2 could be, well, let's look at it on a number line. At least 2 would be 2, 3, 4, all the way up to my maximum, which was a sample of size 7. So it would be all of these. So I could either add all these probabilities or just put in the ones that I didn't look at, which were 1 and 0. So this is an example where they would probably give me my answer as 1 minus the probability that x is less than or equal to 1. So remember the binomial formula that we looked at on the formula sheet. So it would be 1 minus, let's see, so the probability that x equals 0 would be 7 choose 0. I have no successes, so the probability of failure would be 0.95 to the 7th. And then the probability that x equals 1 would be 7 choose 1 times success to the 1 and failure 0.95 to the 7 minus 1 or 6. And it looks like that is answer D. Okay? The next one says, a recent study of the GA upper school student body determined that 77% of the students were in favor of shortening the number of school days in the school year. Mr. Shahas finds this hard to believe, so he decides to collect some data. What is the average number of students, I'll underline that, average number of students he will need to ask in order to find one who is not in favor of shortening the number of days? Okay. So we want to know the mean or expected value until he finds 1, his first success. So we know that this is a geometric distribution. And so since it says 1 who is not in favor, so it said that the probability they were in favor was 77%. But since we're looking at not in favor, we would like that to be 0.23. And since it's a mean or expected value, I know E of x or mu of x for a geometric is just 1 over p. And so here's my answer B. And the last one, roll one 8-sided die 10 times. The probability of getting exactly 3 hits, and we know it's a PDF, is given by. So I know the probability that x is exactly 3. It's a binomial because I have a fixed number of trials. They're independent of each other. The probability of success on an 8-sided die for each number is 1 out of 8. So I would have 10 choose 3. Success would be 1/8 to the 3. Failure would be 7/8, and that would be to the 10 minus 3 or 7. And that looks like this one right here. That's all, folks. See you next time.